Okay, so I'm very glad to be here at these HPC Advisory Days in Lugano. It's the first time that I'm here in Lugano, and with this nice weather, it is really a pleasure trip, and I enjoy really being here. My name is Gunter Roeth. I work for NVIDIA as a solution architect. Solution architect are the first technical level, first technical contact. And my mail is here, Gunter R, @nvidia.com. In case you have any question, any follow-up, anything you want to discuss, you can always send me drop me a mail. So today, this training is done by the Deep Learning Institute. The Deep Learning Institute is really an NVIDIA certified institute. We have certified instructors, we have certified classes, and when you take this class, you will get a certification that you have participated in this lab and so on. Today we are starting, or we are only doing the Getting Started lab. There are much more labs. I think we have over 50 deep learning labs. So whenever you feel that you have something in your company or something in your university, in your department, that you want to get some training done or want to get us involved with the Deep Learning Institute, again, contact me and we can set up all kind of schedules, 1 day, 2 day schedules, 3 day schedules with all different kinds of topics. Once you finish the training, you will get a mail from the Deep Learning Institute asking you to quote everything, so to write your, to give your feedback on the labs. Once you have done this, then you will enable, or then you will give you some more credits to your account, and then you can do a couple of other trainings that are normally, that would be normally paid. They are free. So now let me start a little bit when everything started here with the deep learning. The big bang of the deep learning was 3 things that met together. The first of all, big data. Okay, so today we are living in a big data environment. No discussion about it. Look at YouTube, Flickr, or whatever, video contents, sensors. There are tons and tons and tons of data out in the internet, and we want to make some sense out of this data. Our goal is now to make this data somewhat useful. And then, of course, there is this approach to use deep learning to process this data. We will see a little bit later, deep learning is you train like our brain. So we are able to train neural networks, and they learn to do a certain task. And this technology has already existed since the 80s, but is still today very compute intensive, and it runs very well on GPUs. So if you combine GPUs into the training process, the training today is doable, even on very deep and very large networks. And so all these 3 initial conditions are a little bit the Kickstarter of the deep learning as we see today. So now let us first see a couple of success stories already used in deep learning. So of course we have all kind of what is photo analysis, picture, contents description, and so on. So today deep learning is able to identify scenes, to identify everything in the photo. Deep learning is used also for speech recognition. Skype proposed an automatic English-Spanish translator, real-time automatic Spanish-English translator based on deep learning. Self-driving cars would be impossible without deep learning. It is used all over the place. And of course, it is used in medicine, but in medicine not to replace the doctor yet. But today, when you do, for example, scanners or X-rays, huge data sets are created, and it takes just a lot of time for doctors to steer through all these images. And deep learning will do here, or will find the anomalies that maybe exist. And if there are certain anomalies, then it will point the doctor to say, okay, here I think in this picture, in this radio, in this scan, I think there is some anomaly. Please have a deeper, more look. Image classification, we see here 3 examples. Of course, all what is object detection on a picture. So there is here from Berkeley Vision Lab, they have put a nice object vision demo out. Scene detection can be also done. When you go to this side here from the MIT, so you can describe scenes. And neural networks also not only recognize style, so you can show Baroque painting and let the neural network guess that is a Baroque painting, but neural networks can learn how a certain painter has painted in a certain period. So for example, Van Gogh. And so if you show a photo, a normal photo, and then you select the Van Gogh style, then the neural network will paint this photo as Van Gogh would have painted the scene when he would have seen it today. So this is a little bit the idea of all these here at the Karayev demos. One brilliant use case is also these Pinterest. So I don't know who uses this. Is anybody using Pinterest here? No? No hands up? Well, here, 1. Okay. 2. Okay. So Pinterest is a deep learning application. So you have a photo, and then you can zoom on your photo, this region that you're interested in. In this case here, I would be interested in the flowers. And then you get all the information, what kind of flowers this is, if you want to put them in your garden, where you can buy them, and so on. So it's a very nice application that is running on and using a lot of deep learning behind, of course. Another is semantic segmentation, or fully, and then we will come to the fully segmentation. Semantic segmentation is a pixel-by-pixel classification. So every pixel here that we see in this picture here is then classified according to the semantics. So this is road, this is a car, this is a sidewalk, and so on. So every pixel or group of pixels is classified, and this is working very well with deep learning. And we can do also a fully convolutional segmentation. In this case, we do not have any semantic description any longer, but for example, here the pedestrians would be colored in a certain, in a different color than the cars, and so on. Here on the bottom, we see the road detection as it is going on in self-driving cars. And this one, we can also see here, what we have here, it is called Open Road Net. So Open Road Net is using this fully segmentation to find the street. Then we have in the car, we have a lane net detecting the lanes. And today we also have 3D bounding boxes in the car detection. And with 3D bounding boxes, we get this additional depth information. So how far is the car really in front of me? And of course, we have multi-class object detection all over the picture, because when you drive in a car, you must not only, well, you must of course detect pedestrians, road signs, and all kinds of things. And so these are very, very, very trained, or very good trained networks. I already mentioned Skype, the automatic Spanish-English translation. And here's another example from Baidu, Deep Speech. And here you can see how easy it is to retrain, to retrain on other features. So the first thing that they tried was English speech recognition. So in speech recognition, what you're doing is you have your audio input, and then you try to transform it to some written output, okay? And then from the written output, you can go, for example, into computer processing and so on, what the person has actually told. And so the first thing that they trained here was an English speech recognition with deep neural networks, and that worked very well. And then they took Mandarin, okay? So Mandarin, so they trained it now on Mandarin, just by changing the training set, if you like. And so now it is not only able here in English, of course you have your 30-letter alphabet plus the numbers and so on, so some grammar rules. And in Mandarin, you only have these ideograms here, and so you must learn them all, okay? So I think there are about 5,000 that you have to learn, and it is, it is really easy to take the same algorithm and to retrain it with different data sets. Hmm? Yeah. Yes, yes. All dialects must be then running through a new training. Yeah. Okay, and so once you can do the pictures and you can do speech, well, then you can combine them. And so here, for example, we have a convolutional network that will find us what is in the pictures. And then we have another network underneath that takes as input the things that the first network found here, and will then form a nice sentence with a nice grammatical structure, okay? And so in this case, a girl in pink dress is jumping in the air and so on. So all photos are correctly not only classified, but they're also correctly written in a nice English. Of course, sometimes, like in these dialects, things are not so well. So here a young boy is holding a baseball bat. So that's not a baseball bat. And he is saying that there's a horse standing in the middle of the road. There is not a horse. There's just there's a road, but of course there's no horse at all. So here we have to retrain a little bit and get. Yeah. Okay, so now let us have a little bit of look. What is the software used in the deep learning community? Because this changes a little bit from what is used in C or Fortran. The deep learning community, so let me first start here. So first of all, you want to solve your different problems, okay? So here, for example, computer vision, you want to work with images, speech and audio, you want to work with voice recognition or translation, or you can even do behavior, so sentiment analysis. So are you in a good mood, are you in a bad mood, or this is possible. And then once you want to solve a certain problem, you will choose your framework. A framework is like a scripting language. So very often when you know Python, it is Python-like syntax, and it can always be called from Python, even if, for example, Café behind is C++, so it is implemented in C++, but no one will really program the C++. Everybody will call it from Python or from the interfaces. And there are hundreds of these frameworks today out. The first ones were Café, Torch, Tejano. Today, MXNet, that runs on the cloud, Microsoft CNTK, Google TensorFlow, so these are the newer ones, okay? So, but this list is far from being exhaustive. Of course, we cannot work with every framework provider and make it run optimal on GPU. So what we are doing is, so we are proposing libraries that we just interpose between the actual framework calls and the GPU before it goes to execution. So we will have a cuDNN, so CUDA Deep Neural Network Library that contains a lot of these deep neural network layers. The different layers are optimally implemented. We have cuBLAS, but these are the things you know from HPC, cuBLAS, cuSparse, cuFFT. And since now we have Pascal, we also have a multi-GPU environment that we can easily program for collectives that is called Nickel. So here we see a little bit an impact on the different, so first of all, what is important here is today we have at cuDNN 5. So all this is about two years. So there are about 2 upgrades of our cuDNN per year. This is, of course, required once from the market because the market is trying to run other different architectures and so on. And also we have different GPU architectures. So the cuDNN 5 is the latest that runs on the P100, and the cuDNN 4 was for the M40 and so on. Okay, so here we have digits. You will work now with digits the whole evening. Digits is an easy startup that is able to, because you will train your network with a lot of images. So to do all this image-based, database organization, you can configure your deep neural network. Once it is running, you can also run it in multi-GPU. You can visualize progress and so on. And at the end, you can visualize your layers. But this is what you will see now in the lab. Okay, once we have trained the network, we want to run it on inference. And here we propose a TensorRT software. This has nothing to do with, so this is, has nothing to do with TensorFlow, okay? It's our product called TensorRT. And so what you can do is you can just, once you have trained your network, you want to get it execute as quick as possible on the new device then. And then you can run through a complete optimization of your different network structure. And of course, we have the same for video for the DEEPSTREAM SDK. Now let me present a little bit the hardware. We have one machine that is called DGX1. And this one is really particular thought as a deep learning appliance. It has 8 Pascal, so the latest P100 with NVLink compute. And the NVLink is then connected in a hybrid cube mesh. And you see here a little bit the layout. So you have 2 very, very strong Intel CPUs. You have 512 gigabytes of CPU memory. And you have 4 InfiniBand adapters. So this is the DGX1 that is a deep learning appliance. On the DGX1, we have now all these different frameworks that I mentioned earlier. So CNTK, Caffe, Torch, Theano, and so on. And we implemented this on a containerized way, so with a Docker container, NVIDIA Docker container. And so you get all these different frameworks in a Docker containerized environment. And they are, of course, then highly optimized. And you can run them immediately. And this is, of course, all this goes under the NVIDIA Cloud Management. Today, the container registry is already open now. So to summarize a little bit here, so we have all for the training of the network. When you go through the training process, it's a long, this needs a lot of horsepower, computing power. So this runs best on the P100. When you go to inferencing, meaning once the network is trained and you want to get an answer as quick as possible, then you should go on the Tesla P40 or the Tesla P4. Here we see now a little bit how we position the deep learning. So I already mentioned that we train neural networks. So neural networks are shown here, and they are called deep neural networks when they have a lot of deep layers. Okay, so deep neural networks is always when you have a more deeper number here of layers. Every neuron in this network, so we see here the neurons are connected from layer to layer. There are no connections jumping the layers here. And every neuron just computes the weighted input sum as how it is connected, and then computes an output value. And the output value is then applied normally by a sigmoidal function, so a threshold function, or a ReLU function. You will see this also in the lab. And in this case, we are able now to train it here, for example, on stapler extractors to do staplers. Tomorrow we want to do tomatoes, so we can do tomatoes, or bananas, or whatever. So here we see now a little bit how the training process goes on. So in the beginning, the network has randomly initialized weights. So when I show in supervised training, I have to provide, with every image, I have to provide the corresponding label, okay? And so I show here, for example, the image of a dog. In the beginning, of course, the network knows nothing, so we'll say this is a turtle. So we can compute from here an error. So what would be the right classification? And that is, of course, dog. And then we can backpropagate the error through the network in the same way as we have forward propagated. And we can now backpropagate the error and compute a gradient for all the weights. And the weights are the only three parameters of the network. Okay, so the goal is to find a set of weights that for all input images, they are correctly retrieved. And once we found a set of weights that satisfies this criteria, then we can stop the training. Okay, then we are done. And then we can freeze the weights because now we found an optimal set of weights. And now we can run it in inference. And in inference, it will even, normally when the training was good, it should classify correctly the different images, even new ones that it is seeing. So this will be your work now. So you will train exactly this network here. This is a network from Jan LeCun called LeNet. And it was originally thought to read automatically the checks. But today there are, of course, no more checks. So anyway, but so the initial idea was in 1998 when all this came out that it should read all the different numbers correctly. And now the idea of Jan was to introduce these convolutional layers. So a convolutional layer is just a normal convolutional filter, like we know from image processing. So we run a convolutional filter on the input image and do some extraction here of, in these feature maps here, in order to help the network to understand what is important in the input image, okay? So it will learn these convolutional filters, okay? And because these are just weights. So we will do here, we have a 32 by 32 image. We run a 5 by 5 convolutional filter on it. So this gives us, so we cannot run over the borders. So we will have 28 by 28 here in this first layer, these convolutional feature maps. And this original implementation had 6 convolutional feature maps. Okay, so this is the convolutional layer. The next step is a subsampling. A subsampling is again to help to reduce the number of weights, the number of adaptable parameters. And in the subsampling, what we are basically doing, to say it in an easy way, we take one value over 2. So this means here I have a 28 by 28 feature map, and I will get a 14 by 14, so one value over 2, okay, in the subsampling or pooling area. And then this repeats. So then I have another convolutional layer and subsampling here and so on. And when you go at the bottom of these networks, there's always fully connected neural networks at the end that will find then the correct outputs here. And this is, of course, 10 outputs, because from 0 to 9, we have to correctly classify. Okay, so this is exactly what you will work now in the lab. So here we see a little bit a snapshot now on this convolutional filter. It is just a normal convolutional filter that you run over the input image. And so you have here a 3 by 3 filter, and you sum up those the neighbors, and you compute this pixel with the neighboring pixel with the information of the neighboring pixels. In deep learning, and this is in the convolutional, in the CNN, in the convolutional network, this one here, this filter consists of weights, and this one here is an activation map, okay? But you will see this also in the labs. Here we see how these convolutional filters look after training. And so what we see here, that when we show, for example, here's a car, it could be also any other kind of image. So what the network has learned here in these very high layers to do really this basic filtering, okay? Basic filtering, or those who work already with image processing know that when you run these vertical, horizontal filters over the networks, you do edge recognition and so on. This is exactly what the network is doing. And these filters also have a name. They are called Gabor filters sometimes. And so, but the important thing here is to know is that the network has learned them, okay? I have not imposed them as an extraction step or so. The network has learned that these filters here are optimally to use to extract the features that have to be extracted, okay? And then when you go to the deeper layers, more and more of the original images are reconstructed, and at the end, of course, you have your fully connected layers that do the final classification.